Hello everyone. So we are going to start the part 3 from the topic Coarse Dispersion. So in this topic we are going to deal with some practical aspect which need to be considered while preparing or formulating a suspension in the pharmaceutical operation. So without wasting any time, let's start our discussion. You see, first of all, settling the suspension. What do you mean by settling the suspension? We all know that suspension, it is a biphasic form or biphasic liquid dosage form where we have two phases. One, it is the solid phases, that is the dispersed phase, that is the solid particles. Another one, it is the dispersion medium that is present in a huge quantity. Usually it is generally the water or aqueous medium, right? So you see, the physical stability of any pharmaceutical suspension, it is generally associated or it is concerned with stability. Physical stability is concerned with keeping this particle uniformly distributed, means uniformly suspended throughout the dispersion. If it don't get uniformly suspended throughout the suspension, we cannot say that the suspension is physically stable. I repeat, the physical stability of a pharmaceutical suspension, it is usually associated with keeping the particle uniformly distributed. But we know that there is a law, there is a rule of sedimentation. The velocity of sedimentation, it is generally expressed by Stokes law. So what do we mean by Stokes law? Stokes law is simple. V is equal to d square rho s minus rho naught into g divided by 18 eta naught. So what are these factors? The V, it is the sedimentation. This V, it is the sedimentation velocity, right? D, it is the diameter of the particle. This rho s and the rho naught, these are the densities of the dispersed phase. This is the dispersed phase and this is the dispersion medium. These are the densities, right? G, it is the acceleration due to gravity, and eta naught, it is the viscosity of the dispersion medium. So this is the Stokes law. Now let us have some discussion with this. See, this Stokes law is useful in fixing the factors which can be utilized in the formulation of the suspension. So what are the different factors? See, as we have already discussed, the Stokes law associated with the rate of sedimentation, is associated with the diameter, difference in the densities, right, as well as the viscosity of the medium. So how they affect? So first of all, the particle size, that is associated with the diameter. So if the particle size of this particle, suspended particle, it is reduced to half of the original. Suppose original particle size was, suppose the particle originally it was having a diameter of 4 centimeter. Suppose 4 centimeter. Now if we reduce it to 2 centimeter, then what will happen? The rate of sedimentation, it get decreased by a factor of 4. Means decreasing the size of the particle to its half will increase the rate of, it will decrease the rate of sedimentation by a factor of 4, right? Number 2, it is the viscosity. See, actually higher the viscosity, we know that lower will be the rate of sedimentation. That's a very simple physical attribute. If we increase the viscosity, definitely the rate of sedimentation will be low. Now the high viscosity enhances the physical stability of the suspension by preventing if we do high viscosity, if we increase the viscosity, what it will do? It will prevent the sedimenting, or it will prevent the sedimentation process. It will inhibit the crystal growth, right? And it prevents the transformation of metastable crystal to a stable crystal, right? But however, high viscosity hinders the drug absorption. That also need to be considered. If we increase the viscosity to a high extent, it will affect the drug absorption from the suspension, and it generally creates problem while handling a suspension by a patient. That thing we have to consider. Now the next thing, that is the density, that was written in the denominator part. Now density of the medium. See, the density of the solid used in the suspension, it is generally from 1.5 to 2 gram per cc. Now if the density of the medium is made equal to the density of the solid, I repeat, if the density of the medium means dispersion medium, that is of your water, if we equalize, or if we made the density of the medium equal to that of the solid, then what will happen? The rate of settling becomes 0, means it will not settle. In general, the density medium, that is the medium density, it is generally 1 gram per cc due to the aqueous phase. It never becomes equal to, means 1.5. Generally water have a density of 1 gram per cc. Now you see, thus there is a need to increase the viscosity of the medium. So somehow we have to increase the viscosity. As we have already discussed that the water viscosity, it is generally 1 gram per cc, right? So that the difference in their viscosities become equal. So what we can do? The density can be increased by using different agents. These agents, example of these agents are PVP, polyvinyl pyrrolidone, glycerin, sorbitol. This can be increased. PVP, glycerin and sorbitol, they can be used to increase the density of the medium. Now the combination of these, actually they yield a suspension, and that should have a high concentration, though the improvement in the density is very less. Even after adding this agent, the improvement in the density is very less. Hence it is not a viable factor in that to be considered in decrease of the rate of settling. Now sedimentation of flocculated particles. So we know what are flocculated particles, right? So the extent of the sedimentation, it is quantitatively expressed by two parameters. First parameter, it is the sedimentation volume, or it is also known as sedimentation height. And the second parameter, it is nothing but it is the degree of flocculation. So let's discuss them one by one. So you see, these are actually normally used for comparison of different types of suspension. What are the different types of suspension? Flocculated and deflocculated suspension, and they are generally applicable to flocculated suspension only, right? So the term subsidence is sometimes used to describe settling in the flocculated suspension system or flocculated systems, and it refers to the descending of the boundary between the sediment and the clear supernatant above it. Let us discuss with a practical case, then we will understand. You see, when sedimentation is studied in the flocculated system, we know what are flocculated system, right? Now if we study the sedimentation process in a flocculated suspension, we see, what we see, it is observed that the flocks tend to fall together. Why they tend to fall together? As because they, in the flocculated suspension, the solid particles, they form loosely fitted network. Thus they form togetherly, right? They form a network-like structure. Regarding this thing, we have already discussed in our previous classes. Thus they produce a distinct boundary between the sediment and the supernatant layer, right, in the flocculated suspension. Now the liquid above the sediment, it is clear in the flocculated suspension, means the supernatant in the flocculated suspension, it is clear, because even the small amount of the particle is present in the system, they are associated with the flocks only. Thus in a flocculated suspension, we generally get two layers after allowing the bottom to settle down for a while. In the bottom layer we are going to get the settled floccules, and in the top layer we are going to get a clear supernatant. Now such is not found in case of the deflocculated suspension. Why? Having a range of particle size, in which in the deflocculated suspension, the suspension have a wide range of particle size, and there this type of demarcation of these two type of layer, means the layer of the settled floccules and the layer of the supernatant, it is not seen in the case of deflocculated suspension, as because in the deflocculated suspension, the settling down or the rate of settling or the velocity of the settling, it occurs with that of the Stokes law. So what actually Stokes law states? As per the Stokes law, you see, larger particles settle more rapidly than the smaller particles. So what will happen in the deflocculated suspension? The larger particle will settle down immediately in the bottom, the smaller particle will meet the supernatant. Thus you are not going to get a clear supernatant. Clear? So you see, no clear boundary is formed, and the supernatant, it remains turbid for a considerably longer period of time in case of deflocculated suspension, due to the difference in the particle size of the suspended particles. The heavier particles, they settle down immediately, while the smaller particles, they remain suspended for a long while in the supernatant range. Thus, you cannot demarcate the two layers in the case of the deflocculated suspension. So, whether the supernatant liquid is clear or turbid during the initial stage of settling, it is a good indication of whether the system is flocculated or deflocculated. Why? If the system is flocculated, then definitely you are going to get a clear supernatant. That is the upper layer, clear upper layer, right? But if the suspension it is deflocculated, you are not going to get a clear layer. The next thing, it is the sedimentation volume. So the sedimentation volume, it is designated with F, capital F. It is defined as the ratio of the final, or you can say ultimate volume of sediment. That is ultimate volume of sediment. It is designated with VU to the original volume of suspension. That is the V naught. Ultimate volume of sediment means after settling down of the floccules to the initial volume, means before separating what was the volume and before settling. And HU, it represents the height of sediment. Thus you can take it as a equation here as the sedimentation volume F is equal to, this sedimentation volume F is equal to, this is what? This is the final or ultimate volume divided by that of your original volume of the suspension, or this is the ultimate height divided by original height of the suspension, right? Now you see, for ideal suspension, actually these two values, the VU and V naught, it always become equal to one another. So F is equal to 1 for ideal suspension. But such cases generally don't encounter in our practical life. So normally the value of F, the value of F, it lies between 0 to 1. And in general, higher the sedimentation volume, better is the physical stability. We know that higher is the sedimentation volume, better will be the stability of the suspension. Now the degree of flocculation. What is the degree of flocculation? It is designated with simple beta. You see, the sedimentation volume, it gives only a qualitative account of the flocculation. As because this sedimentation volume, it lacks of meaningful reference. What it actually gives, the degree of flocculation, it just gives the, what is the degree, it means how fast it is getting flocculated, right? So a more useful parameter of flocculation, it is with beta. Beta, it is the degree of flocculation. So degree of flocculation, it is designated with an equation. But before that, going to that, let us have some practical aspect. Suppose if we consider a suspension that is completely deflocculated. Here, now the ultimate volume of the sediment will be relatively small in the deflocculated system. Why? We know that because in a deflocculated system, the suspended particles, they never form loose network and they never settle together. In the deflocculated system, what actually happens? The heavier particles is settle down fast, and the lighter particles, they used to remain suspended in the supernatant, right? So writing this volume V alpha, that is V alpha, we can have one value F. In the deflocculated suspension, we can write this equation as F alpha is equal to V alpha divided by V naught, right? So where this F alpha, it is the sedimentation volume of deflocculated suspension, and this V alpha, it is the sediment, it is the volume of sediments, right? And the degree of flocculation, it is the beta. Therefore, it is the degree of flocculation beta in the deflocculated suspension can be defined as by this following equation. Beta is equal to F by F alpha. So now just put the value. We know that F is equal to VU by V naught, right? And F alpha is equal to V alpha by V naught, which is equal to actually VU by V alpha. Thus you see, the degree of flocculation is a more fundamental parameter. I repeat, the degree of flocculation is a more fundamental parameter than F. Thus, because it relates the volume of the flocculated sediment to that of the deflocculated system. I repeat it once again. You see, the degree of flocculation is a more fundamental parameter. Degree of flocculation, that is the beta, as compared to that of the F. We generally consider the degree of flocculation beta. Why? because the degree of flocculation, it relates the volume of flocculated sediment to that in a deflocculated system. Thus, you can write this beta as beta, that is the degree of flocculation, is equal to ultimate sediment volume of flocculated suspension divided by ultimate sediment volume of deflocculated suspension. I repeat, beta is equal to ultimate sediment volume of flocculated suspension divided by ultimate sediment volume of deflocculated suspension. So I hope you have enjoyed the class. If you like my video, just press the like icon. You can share this video and you can subscribe to my channel. Thank you once again.